Okay, this first unit focuses on something that we call induction, which is a method for proving things. It's not like two-column proofs. Okay, the kind of nice thing about induction proofs is that there's one method for proving things by induction, and it's kind of the same 3 steps every time. Okay, it's just a matter of what goes on during those 3 steps that might differ from proof to proof. But just to illustrate the difference, so far in high school, you've probably done proofs that look something like this. So we'll do one.
Oh, no.
And you're given some information like that AC bisects BD and AB parallel to DC, and you're supposed to prove, well, there could be lots of options, but let's say
Is that BC or
D. Let's say maybe prove that segment AE, which is going to be the intersection there, is congruent to CE. Okay, so what you've done so far is basically prove these kinds of things in geometry. Do you remember what method or what it was called when you did these? Two-column proofs, okay? Which looks something like this. I mean, in my geometry classes, when I teach this, I usually say, start with the given information and mark it. So AC bisects BD. That means that if AC bisects BD, that means that this segment and this segment are going to be congruent, right? Does that sound familiar?
yeah.
What's that? Okay. You sure? Okay. AB parallel to DC. So if this segment is parallel to this opposite segment, we know that alternate interior angles are congruent. So we have these angles congruent. We also have these angles over here congruent. And then, let's see. And I guess really that's all we need. We could mark some other things congruent, but just from that, if you guys remember, there's a postulate that says that if 2 angles in order and then a side are congruent to the same thing, that proves the triangles are congruent. That was called, not very fancy, AAS postulate, right? So that's how we're going to do it. So if we were to do this proof, we'd say, well, first, from the fact that AC bisects BD, I concluded something else. So actually, I'm going to write out all my statements first. The fact that AC bisected BD, what did that allow me to do in the picture? Mark. Very good. So I'm going to say DE congruent to BE. So that's what the given statement allowed me to do. And next I went on to this other given statement, which is that AB is parallel to DC. And then what did that allow me to do? A couple of them, right? It allowed me to say that angle BAE is congruent to DCE, and also that angle ABE, bless you, is congruent to CDE. And now after that we said, well look, now we can say that these 2 triangles, this triangle here and this triangle there, that those are congruent because I have the angle-angle side, right? So I'm going to say triangle, let's go from A to B to E. and then keeping the order the same, that would be C to D to E. And then once you prove triangles were congruent, then you could say that the corresponding parts were congruent. So then we would say what we wanted to prove, which is ultimately that AC is congruent to CE. So this is what the format for the proof looks like, and then you just had to explain why all this stuff was true, right? So the explanations would look something like what? This is given, good. And then what would our explanation for the second step be? Definition of bisect, or if your teachers were strict about it, they could say if AC bisects BD, then DE congruent to BE. Or you could just say it's a bisector, so that means that they're congruent. Step 3, that was given. Step 4, these angles were congruent because, not opposite, but alternate. Yeah, so we'll say if AB parallel to DC, then let's just say alternate interior angles are congruent, and that's good enough. And then we concluded that these two triangles are congruent by angle-angle side postulate, which is a common geometry accepted reason for saying that triangles are congruent. And then once we had the triangles are congruent, your teachers probably said you could just write CPCTC. Does that sound familiar? Which stood for corresponding parts of congruent triangles are congruent. Okay. How many of you love those? Those were the funnest thing in geometry. Nobody? Really? Aw. Well, the good news is we're not going to do those in this unit, but I just wanted to do one so you can kind of remember that this is what proving things looks like in geometry. But this is really only an accepted thing in geometry. I mean, you don't do two-column proofs elsewhere. Okay? In the real world, there's several methods to prove that statements are congruent or that something is true. One of those is just to do deductive reasoning, which is a direct argument. Like if this is true, then this is true, and if this is true and that's true, then this must be the conclusion. That's a direct argument. There's also something called the contrapositive, which is another more complicated way to prove things that you'll learn about later. You can do a proof by contradiction, which sounds like what it sounds like, or which is what it sounds like, where you get a contradiction, which then means that the other statement or the opposite of it must be true. And then there's this other thing that we call induction. Okay, so now we're going to have lots of general statements, not necessarily related to geometry, but they might look like something like this. So let's just look at a sequence of numbers, like 1 plus 3 plus 5 plus, what's the next number?
7.
And so on. And let's say I go on for a very long time. And now, the good news for you guys is that over here at the end, they'll tell you what the formula is that spits out all of these numbers. Okay? I mean, we could even find it right here. What's the difference? From each number goes up by 2, so that'd be like almost having a slope of 2. We don't use x's, we use n for our variable. And now if you kind of look, if I plug in 1, what do I get? 2. But I want it to spit out the first number. So if I subtract 1, now when I plug in 1, I get 1. Everybody see that? And if I were to plug in 2, would it spit out the second number? And the third number? Okay. So this will be given to you, but eventually we're going to have to find these kinds of formulas later, so that's why I'm kind of going through that. Okay. So the idea here is to come up with a conjecture. So we're going to go from start to end. What is this going to become? We want to know what this ultimately equals. Okay? So what we'll do before we introduce what induction looks like is just kind of explore. For n equals 1, we got 1, right? For n equals 2, we're really adding the first two things together. So that's 1 plus 3, which is 4. And if I wanted to do the first three numbers, I would do 1 plus 3 plus 5, which is 9. Anybody see a pattern yet?
Multiplied by
Going up by the. It's going up by 3 each time. It's going up by 2 each time.
What's going up by 2 each time?
Like y. The y coordinate.
The y coordinate's going up by 2 each time?
Yeah.
If you were to plot it as coordinates.
Or it's going up by double the amount, or like 2 plus the number it's going up. I don't know how to say.
So what would the next number be?
16.
16. Okay. I'm not sure what you're describing yet, but I agree that it is going to be 16.
Were you asking what it was going up by?
Or if there's any other relationship that might be easier.
If you take 4 and then you add 5 squared, and then if you take 5 plus 1, so like add by 5 and then by 6.
Okay. So you guys are explaining lots of different connections. Here's ultimately what we want to do. Okay? Take this value. How do we get that? Take this value. How do we get that?
square.
Ooh.
Square.
So does it look like... So if I were to add up the first 5 numbers, I should get 25 for this pattern, right? Okay. So that's a reasonable conjecture. Let's write that down. So our conjecture is that if we'll do fancy words now. The sum, that means we're adding things, right? Of the first whatever numbers, we'll call them n. The first n, and these are all what kind of numbers? All odd. So the sum of the first n odd numbers is what?
The square.
The square of whatever n is. So that's our conjecture. Now, believe it or not, we can't just prove this by saying, look, I did the first 100 examples and it works. Okay? All that proves is that the first 100 examples work. It doesn't prove anything about the 101st example or the 1000th example. Okay? So here's the idea behind induction. Okay? Oh, good call. Everybody have this written down? Okay. So induction proofs look something like this. And then we'll apply this method to proving that last example. For every natural number n, we have a statement that we're going to call P sub n. In other words, that's the conjecture. Okay? So for every natural number, we have a conjecture. Like if I were to add the first 8 odd numbers, the answer would be the square of 8, which is 64. That's what our conjecture is. Now, to prove that, we have to do 3... Let me use a different color. We have to do 3 things. Okay? Number 1. Show that P sub 1 is true. This is called the basis step. And if, for lack of better words, all of this is just showing that the first case actually makes sense and works. Okay? It's like getting your feet wet. Before you step into the pool or dive into a pool, I know it'd be a rush to just kind of dive in not knowing what to expect, but I would guess that a lot of you maybe feel around to see what the temperature's like and then get in, right? This is what we're doing. Okay? We're just kind of feeling the statement. Sounds kind of weird. But we're feeling the statement out to see if it actually makes sense. What they're telling us works a little bit. Okay, that's what the first step is. Second step. Once we know that, okay, look, it works the first time, the idea is that we're going to suppose or pretend that P sub k is true, where k is any case. So we're going to pretend that whatever case you want works. Okay? And if we can show that the next case, P sub k plus 1, is true, then we're on to something. Okay? This is called the inductive step. Okay, and if you want to think of a visual, this is kind of like if you imagine some dominoes. Everyone know what dominoes are?
What?
Has anyone ever set them all up?
Yes.
I'm sure you have. And you just kind of try to knock them all down and you create patterns and
Like a house and then
yeah.
it goes up.
Okay. Now if the dominoes are arranged correctly, if you knock one over, what's that one do? Well, let's slow down. The first one knocks over the second one, and the second one knocks over the third one, and so on and so forth, right?
You should turn off the
Okay,
video.
this is pretty much what we're doing here. We're saying, you know what? Imagine that every single step of the way is like a domino, and we're picking up this at whatever step you want or whatever domino you want. So if I pretend that for the first 100 dominoes they've all fallen over, if I can prove to you that the next one's going to fall over, that'd be like saying that I have 1,000 dominoes and then showing that the next one after that falls over. Or if I have 1,000,000 dominoes, which would be some site, that if the 1,000,000 dominoes fall over, so will the next one. Okay? That's a very powerful statement, okay? Which then pretty much shows us that, and this is the conclusion, that's the last step. The conclusion then is that if I've proven that no matter where I am in the sequence of steps, that if I can prove the next step also works, then we can conclude that P sub n is true for every single case, for all natural numbers. Okay, so these are your three basic steps. So first we show that the first case works. Then we say, all right, let's say that the first however many dominoes have fallen, k, let's say that they all fall. I'm going to show you that the next one is guaranteed to fall no matter what. And if that's true, then that means that they all must fall. Yes?
Natural numbers, that's just like...
Counting numbers.
Yeah.
Good question. Natural is just counting. So 1, 2, 3. No zeros, no negatives. Okay. So let's actually go back to what we were trying to prove. We had 1 plus 3 plus 5 plus 7 and so on up until whatever. And we said that if I wanted to add the first however many odds, I always got just the square number. So if I wanted to do the first 7 odds, I'd get 49. Okay? So here's our proof. So first we have the basis step. Okay, so it's not a 2-column proof. We're actually going to write sentences and show things so that things make sense. P sub 1, that's like the first case, right? I have two sides to this equation. I have the left side and I have the right side. On the left side, what would I have for just the first case? Just 1. So I'm going to write literally left-hand side equals 1. And on the right-hand side, according to this formula, I'm supposed to take that number and then square it, and I get 1. Bless you. So we have just proven that the first case works. We've tested the waters. Nothing crazy going on. It seems like it makes sense for the first case. Okay? Okay, so now our inductive step is step 2. Okay? And we're going to use this language that we have here. Suppose that p sub k is true. So I'm going to write, suppose p sub k is true. And just for you and for the reader, now we'll explain what that looks like. So that is the statement that 1 plus 3 plus 5 plus 7 and so on. Yes? Oh, you wanted to move it up? Sorry. So if we're saying that, hey, this thing works for k, then really what that means is that if I take the first k odd numbers, so all we're doing is literally replacing n with k, that I should get on the right-hand side not 1 squared, but now k squared. Okay, we're assuming that this works. Okay? So now we need to show, or we will show, that p sub k plus 1, the next case, is also true. Whoops, just mixed up my letters there. So what does that mean? Well, that means that I have all of these numbers, and then I'm just going one number after that, right? So I'm going to write that down. 1 plus 3 plus 5 plus 7 plus and so on. I'm still, and by the way, just so everybody makes, or just so we're sure that everybody's on the same page, this is the first number, second number, third number, fourth number. What's this number right here? Which in this case is the kth number. Okay? So we're going to go all the way to 2k minus 1. But now we're going to add in the next number. So if currently we're at k, but we're going one further, then that means that I should be able to, instead of using n, I would use 2 times not k, but k plus 1, since that's the next number. Okay? I'm just following the formula here. And then on the right side, instead of doing k squared, I would have to do k plus 1 squared. Okay, so our goal is to prove that now this is going to have to be true. Okay? Well, here's the big leap that we're going to make. Now we're going to use our inductive hypothesis. Okay, so by the inductive hypothesis, now I'm going to switch some colors again. We know what these equal, don't we? What does the first k numbers add up to, according to our hypothesis at the beginning here? It adds up to k squared, right? So this red box becomes k squared, and now I still have this 2 times k plus 1 minus 1, and we're still trying to show that that's k plus 1 squared. I put it right there, that's fine. Okay. So does everybody see what I did there with the red box, using our supposition or hypothesis that the first k numbers add up to k squared? So I took our first k numbers and made it k squared, because we were pretending that worked, right? So now our job is just to show that this side is exactly the right side. What could I do on the left-hand side to see if this actually works? Yeah. So we have k squared plus 2 times, or 2k plus 2 minus 1. We're almost done. If you can stay for just 30 seconds, I'd appreciate it. What do we get on the left? 2k plus 1, which that's actually exactly the right-hand side. Do you guys see how that worked? Okay, so that's the inductive step. We've now shown that, hey, the first k things add up to a k squared. If I add in one more term, it does equal k plus 1 squared. So now what we say at the final step, the conclusion, is that 1 plus 3 plus 5 and so on, up through 2n minus 1, does in fact give us n squared, and we just say by induction. We use the method of induction to prove it, and that is the end of the proof. Okay? Work through the homework. We're going to practice a little more tomorrow, okay? But that's the basic idea.